Okay. Hi, everybody, and welcome to the first seminar for XFC 2024. We have a number of seminars this year to help students get off the ground in terms of developing their systems and how to implement them in the game Kessler. We have this one, which is on fuzzy systems and fuzzy logic, with a brief intro to fuzzy trees. Next Friday, we'll have another on gradient-free optimization with a large focus on genetic algorithms. After that, we'll have a seminar that introduces everyone to the game itself, named Kessler. Then after that, we'll have a few seminars from other professors that are involved in XFC, including one on backpropagation, reinforcement learning, and then one on explainability in fuzzy systems. We'll also have another meeting after that on the competition itself, but that one is not so much a seminar as it is a general meeting. I'm going to go ahead and get started with today's. We'll go over some slides and some different topics, but I'm going to leave plenty of room at the end for discussion and questions. As always, this is being recorded and it will be uploaded to the YouTube channel afterwards. If there are additional questions or discussion points, as always, please put them in the Slack or email us organizers. The Slack, I pitch it every talk, but I'm going to go ahead and do it again. Please join the Slack if you're involved in the competition. That's where we have most of our day-to-day communication with the teams. It's much easier to get quick feedback or help if that's needed. So without further ado, let's go ahead and get started. I also want to highlight that these slides were provided by Dr. Kelly Cohen, or some of the slides were provided by Dr. Kelly Cohen at the University of Cincinnati. He's heavily involved in both NAFIPS and XFC. He's been a cheerleader and helped out with a number of things involved with the competition. And these slides are originally from one of the classes that he teaches at the University of Cincinnati in fuzzy control. So let's go ahead and get started. Fuzzy logic is really an extension of classical Boolean logic. This slide in particular is talking about state-of-the-art solutions for a number of different things involved in the realm of what's called soft computing, including both learning algorithms and mathematical optimization, but then also things like function approximation and knowledge representation. So fuzzy logic sits somewhere in there, typically under what people call expert systems. The reason why these were referred to as expert systems was because when fuzzy was originally introduced back in the 1960s, they were used in a lot of industrial control systems where it was difficult to construct an explicit model of the system. But it was relatively easy to encode information, or there was a lot of useful information from the operators or people with a lot of experience in those systems. And so having the ability to encode that expertise from those operators to be able to control those systems was very beneficial. Due to the nature of fuzzy logic also, it lent itself well to encoding that information because of its knowledge representation in the terms of an input to output mapping that is in a linguistic representation. So you can have actual English language sentences that represent your input to output flow. So that's sort of what really drove the initial development of fuzzy inference systems and fuzzy controllers, which we'll see towards the end of the presentation. But fuzzy logic is also useful in a number of other areas. It's an extension. It's higher order representation than Boolean or classical set operations as well. And so it has a number of different applications. The main focus of the competition, though, is both using it as a function approximator, but also the knowledge representation in that linguistic form is useful for the explanations, hence the X in XFC. So it is a good method for being able to implement an AI agent in systems like this and still be able to get that knowledge back out. So fuzzy logic, as I mentioned before, is an extension of Boolean or classical set logic, where instead of things being just belonging to a set or not, it's just a binary option of yes or no. Fuzzy allows you to have higher order representations of that, so you can have a scale from 0 to 1 of membership in a set. So one example that gets used quite a bit is what constitutes a weekend in terms of the days. Is Saturday a weekend day? I think pretty universally people would say yes, Saturday is 100% a weekend day. Yes, it's in that set, it is fully in that set. So its membership in the set of weekendness is 1. Would people consider Tuesday a weekend day? Well, it's in the middle of the week. It's not adjacent to the weekend days that people typically consider weekend days. So no, it is not a weekend day. And so we say the membership in that set is 0. Is Friday a weekend day? You could say that no, technically Friday is not a weekend day, but Friday does have some of the characteristics that are associated with typical weekend days. You don't have to do preparation in the evening to be able to get up early the next day for certain things. So people often consider Friday mostly a weekend day because even though you may be doing things like going to work or not treating it completely like a weekend, the evening most definitely is considered a weekend evening. And so just having 1 or 0 doesn't fully encapsulate the information about the characteristics of Friday that we want. And so that's really the benefit of having something like fuzzy is you can then classify Friday as something along that scale. So in this case, we're going to say, yeah, it's 0.8 in the set of weekendness. We're saying for the most part, yes, but not completely. You still have to get up early in that morning. Typically, you're going to work if you have a typical Monday through Friday job. So not completely a weekend day, but also not only a weekday. How about Sunday? Similar to Friday, yeah, Sunday is mostly a weekend day because you have a lot of the same characteristics, except, yeah, and in the evening, you're going to have to do preparation for the work week and go to bed earlier and things like that. You don't have as much freedom. So Sunday being a weekend day, we're saying is somewhere around 0.95, where yes, it is, but not nearly as much, not quite as much as Saturday. Saturday is just complete full membership and weekendness. So this is just an early example into what fuzzy offers as opposed to classical set theory. This is a visual representation of this, where in classical logic, where you can only represent weekendness 0 to 1, or 0 or 1. We see that Thursday and Friday, they're not technically weekend days, so we just say no, they're not in the weekend set at all. They're just 0. And Saturday and Sunday are the only 2 that are weekend days, and they just have full membership in that. And then we see Monday again back down to 0. Well, that's not, that doesn't fully encapsulate the information. So if we allow for values in between 0 and 1, we can get a much more representative distribution of membership in the weekendness set. And so if we look at this side, this is representing a more fuzzy approach to this, where we say, well, Thursday even has a little bit of weekendness associated with it because there are a lot of evening events that tend to get put on Thursday evenings. People tend to take Fridays off much more than other days. So it does have some amount associated with it. It's not typically a pure weekday. Friday is much higher because of the things that we discussed earlier. So it's somewhere up here on this scale. Saturday, as we've discussed, is full membership. Pretty much nobody considers Saturday to not be a full weekend day. It's the day for doing weekend events. Sunday, like we mentioned, is almost a full weekend day, but has some qualities that make it a little bit less so. And then, of course, Monday, everybody's a big fan of Mondays, as we all know. And Monday is back down to zero, where I don't think, in most cases, if there's not a holiday, Monday is not associated as a weekend day. We can go a bit further. Rather than looking at these discrete options for days, what if we wanted to just look at time throughout the week on a continuum? We could have these functions that describe the entire space throughout the week, where in classical Boolean logic, we see that up until where Friday transitions to Saturday, we have 0 membership in that set, and then it immediately discontinuously jumps to 1, because now you have membership in the set starting on Saturday through the end of Sunday, and then back down to 0 at the beginning of Monday. So this is what's known as a membership function. This is a visualization of a function that describes your membership in the set of weekendness. And in a Boolean membership function like this, or a classical set, you just have these discrete jumps from 0 to 1 and then back down. So you just have these step functions that go all the way up to 1 and then back down. Just binary. What fuzzy allows you to do, though, is you're not limited to this. You can have a function that describes essentially any shape that determines your membership in a set. And so going along this continuum throughout the week, you can have this gradual increase in weekendness as you approach Saturday, and you get full membership once you reach some value between Friday and Saturday, and then continues on through most of Sunday until towards the end of Sunday, it starts decreasing quite heavily, back down to 0 on Monday. And so this is just a quick visual example of how you might want to describe membership in a set with a function that is not just Boolean. This is one reason for doing this is there's often a lot of uncertainty associated with the characteristics that you're measuring, and being able to account for that uncertainty in a much more granular way is very useful in many scenarios. And that is one reason why having these different shaped membership functions is very important. There's another aspect of this that we'll see a bit later, which is in classical set theory, when you have overlap in these sets, the overlapping region as well is also a classical set, in the sense that you can belong to one or both or neither. Whereas in fuzzy sets, although that's also the case, you can also get a more granular representation of the creative membership of all of those sets. And how much they overlap is another point of useful information that you can then use to make inferences. You can then use that to then say map to an output action. So let's say that you wanted to decide if you were going to perform a particular activity, like go to a certain restaurant, but you only want to do that on the weekend. Well, you would then say, well, based on the current time, whatever the input value is, let's say it's Friday afternoon, whether you want to go to this restaurant or not. If my weekendness is above a certain amount, then yes, I will go to the restaurant. But if not, then no. And what we'll see here is that this really in classical set theory, this only allows you to do that on Saturday and Sunday. That's it. Whereas you can make a much more nuanced decision based on the more granular information that fuzzy provides. One thing I want to highlight before we move on to the next slide is this is different from probability. Probability is describing the likelihood that you exist in a Boolean set, a classical set, in the future. Or it doesn't necessarily need to be in the future, but it's something that has not yet been measured. You don't have the outcome yet, but you're saying that This is the prediction that of your membership in a set or not, but it's only one or the other. Whereas fuzzy says, well, you can go a bit further than that and say, even if you've already measured, you can say that, yes, I have measured, but I only exist in this set this amount because of these overlapping characteristics. We can see a similar thing with seasons of the year. We could describe the 4 different seasons as Boolean sets, classical sets, where your degree of membership is just 1 or 0. And you transition from one to the other in this binary manner where you reach a certain point, let's say June, where you just switch from spring to summer. Now, I'm in Ohio, and although some may say that that's how it works sometimes, we all know that that's not really the case. It doesn't immediately go from 50 degrees and raining every single day to 80 degrees and sunny every single day. There is a continuum where you gradually change. And in fact, a better representation of this would be if there were overlap even between the classical sets. There would be a question of how to resolve that overlap, though. On the fuzzy side, we see something that's much more representative of what we actually experience during the different seasons, where you have not just overlap between the sets that describe the different seasons, but you also have these membership functions that describe a continuum of the characteristics associated with that season. And in this case, those characteristics could be things like temperature, the amount of precipitation, that sort of thing, humidity, whatever. But that's really what we're talking about, is you're really attempting to measure some your associated characteristics and then map that to a set of values that represent some portion of your input space. And so we see the overlap of all the different seasons, and then you can then use that to do information processing as well. So one of the proponents of fuzzy in particular, this is from Bart Kosko. He was a big proponent of fuzzy thinking in terms of being able to reason about things when you have imprecise or uncertain knowledge. But it's not meaningless. You're still getting valuable information, and you need to act on that. So how do you account for that uncertainty or that vagueness? And this happens in humans. Humans oftentimes reason with scant evidence and vague concepts. We have rules of thumb. People often act on their own beliefs, which may not be precise. They may not even know why they're acting on those beliefs. They may have hunches and guesses that may turn out to be accurate. They're not even sure why. And so they do possess valuable information, but they're not precise. You can't represent them as an explicit mathematical construct in a lot of cases. So fuzzy is a way to help deal with these types of pieces of information. Natural selection in humans involved with this uncertain cognitive calculus. Humans are, well, I should say the human brain is very good at approximator. It's very good at getting you approximate solutions very quickly by associating certain things, but it does so in a very fuzzy way. And we use this fuzzy calculus to run our lives, careers, etc. And we do employ the products of exact science as decision aid tools. The final control remains fuzzy. And what we mean by that is similar to the concept of natural language. Natural language compared to formal languages or mathematical languages or even coding languages are very imprecise. They have these vague concepts that are associated with words and sentences that are extremely useful and very information heavy, but being able to use those in a mathematical way is difficult. And so being able to account for that is important. This sort of leads into the next topic, which is precision versus significance. A lot of times there is a large focus on precision in terms of being able to measure and represent something very precisely in terms of its characteristics. However, those characteristics don't necessarily lend themselves towards significance as it relates to knowledge representation and decision making. A fun example of this is you have some object that's falling towards a person, and another person is attempting to warn them at this, and this person is providing them information that is very precise. They're saying that this 1,500 kilogram mass is approaching your head at 45.3 meters per second. And although they're correct, or we'll assume that they're correct, they have some sort of state estimator that's very accurate in getting this information, and it is of course important for them to relay information of the danger to this person that is about to get hit by this object. This doesn't help them in terms of how do I then use that information to make a decision about how to act. And so instead, we have this other situation where instead of relaying all of this very precise, granular information to the person, we instead just give them a directive that says, look out. We want to alert them to the situation and ensure that they have, even though this is a vague concept, look out doesn't tell you exactly what to do, but it tells that person to be alert and that there might be something that they need to pay attention to and make a decision and act on. And so that's really what we're getting at is you can provide precise information and that's extremely useful in a lot of cases, but especially when dealing with humans and human operators and as we'll see in some of the cases in the competition, human designers, in a lot of cases, and actually for the explanations during the competition, the explanations that the AI agents will be outputting, it's not going to be relevant necessarily for one of the agents to explain in this much detail the state information of, say, one of the asteroids or it's the ship that it's controlling, as opposed to something at a higher level representing the overall situation, such as the threat level of an asteroid or something like that. And so that's really what we're attempting to capture here. These are just some quotes about fuzzy and that from famous mathematicians and other folks or physicists. Henri Matisse said, "Precision is not truth," which is often the case. You can be very precise and be very wrong. I find myself doing that, every so often. Sometimes the more measurable drives out the most important, and that's the case too. This also comes into observability and controllability, and for those that are have a focus on dynamics and controls, that there's often a case where if you can get a very accurate measurement, there's a bias towards using that measurement because of its accuracy, even though it may not be relevant to the decision you're making, or as relevant as some other information you may be able to extract. Even Einstein said, as far as the laws of mathematics refer to reality, they are not certain, and as far as they are certain, they do not refer to reality. That's a consequence of the universe we live in. And the founding father of fuzzy logic, Lofty-Zada, said, as complexity rises, precise statements lose meaning and meaningful statements lose precision. And so what we're really talking about right here is a hierarchy of semantic meaning, such that if you're if you're being extremely precise, that loses semantic relevance to the person or the agent that's taking in that information, really because you're at too low of a level to act on that information. So I've already mentioned this, but let's go through some of the origins of fuzzy. Fuzzy logic was invented in the mid-60s by Professor Lofty-Zada. He was at Cal Berkeley at the time. Allows computers to model the real world in the same way that people do in terms of shades of gray, or being able to blur the lines between different concepts. That was really the driving factor behind his developing of it. It has the ability to deal with situations in which one may not be able to make a sharp distinction between the boundaries of application of rules or constraints. It's unique in that it's able to simultaneously handle numerical data as well as linguistic knowledge. We'll see that quite a bit in the competition, especially when we start getting into things like machine learning using fuzzy systems, because you may use a combination of domain expertise based on what you know about the game itself, and you can encode that in your fuzzy system. But then you may want to also take in numerical data and modify your system, or process it, not just modify it in terms of machine learning. And so it can do both. It is typically, I'll say typically, it can be linear, but it is almost always a nonlinear mapping of input data into output data. And by default, I want to highlight here, fuzzy systems are deterministic. That's not always the case, and you can certainly have non-deterministic fuzzy systems, but most flavors of fuzzy systems are both deterministic and nonlinear. Of course, there's always the caveat that, some non-vanilla system may not be that, but yeah, most typically they are. And by the default examples you'll see in a lot of texts are. So traditional and crisp logic, founded in, or not founded, probably the better way to say it is discovered in 300 BC, or the construct was created is even better way to put it, by Aristotle. Formulated the law of the excluded middle, which is a very important topic in classical logic, which is now the principal foundation of mathematics. And that is the concept that X must be in a set of A or in a set of not A. And that goes back to what we're talking about with those, if you remember the visualization between different sets, classical sets, you can only have full membership or no membership. There is no between. So it's impossible to be in both set A and set not A by definition. We've already gone over this. I don't want to harp on fuzzy logic again. We're going to move on a little bit further and talk about the motivations. So some of the motivations for fuzzy are to alleviate the difficulties in developing and analyzing complex systems encountered by conventional mathematical tools. A typical example that is used for this is in terms of dynamic systems. If the properties of your system are slightly off, in terms of, let's say, mass or moments of inertia, things like that. The equations of motion of that system they would be incorrect and one reason they're incorrect is because of the amount of precision that they have. You can account for this with fuzzy systems in terms of being similar to the original system, but still being able to use that information to act in some way. And we also know that observing human reasoning, we know that we can utilize concepts and knowledge that do not have well-defined and sharp boundaries. So we know that's possible. And so one of the motivations for developing fuzzy and fuzzy systems was to be able to reason in similar ways that humans do and account for that uncertainty. Oops. Okay. I'm going to go and skip over this slide. So why is it beneficial? Well, fuzziness in general is beneficial for complex systems that are difficult or impossible to model. Models are almost always very high precision representations of your system. Well, they don't have to be, but being able to reason about the information or the things that are happening within the system is useful, even if it's difficult or impossible to model in a traditional way. When I was talking about those industrial control systems, that was one of the prime examples of expert systems that humans developed and used. And it's very useful and very practical in many situations to use those human observations as inputs, or as using that information to generate a fuzzy inference system that can then reason automatically using that. And also systems that are naturally vague, like in behavioral and social sciences, things like that, where getting precise measurements is extremely difficult or maybe impossible. And it may be the case that being able to account for overlap in the data, or sorry, vagueness in the data is necessary. I've already mentioned this, but we'll talk about it again because it's often confused. People often confuse fuzzy logic and probability and say they're the same, or fuzzy logic depends on probability, and that's just not the case. They both deal with measuring membership in sets. Probability again is measuring the likelihood that you will exist in a classical set with full membership or not, and fuzzy is saying after the measurement has occurred, how much membership do you have in this set based on these vague characteristics? Some milestones in fuzzy history. First article on fuzzy sets was introduced in the mid-60s, so it's been around for quite a while. It has a good heritage. And the first fuzzy logic controller, so the first implementation of fuzzy logic to control some process, was in 1974, so quite a while ago. There's been quite a bit of development since then. Throughout the 80s and 90s was fuzzy's first hype cycle, I'll call it, where it was being introduced and used in mainly industrial control applications, but then extended on and used in a lot of machine learning situations as well. We'll talk about that quite a bit more next week during the gradient-free optimization talk. But fuzzy controllers have been used in a number of different situations, most famously in Japan. Japan has used fuzzy to great effect in a number of different systems, including a lot of their high-speed train control systems, home appliances, including rice cookers. In fact, I think most of the top rice cookers that you'll find online, at least the Japanese brands, still employ fuzzy in the control software itself. Pardon me. And one reason they did this was because when cooking the rice, there were a number of different measurements they were taking, the moisture content, the temperature, and a few other things. And they were able to directly encode what they knew about cooking rice into that control system, such that they can make a very good automated rice cooker just using that. And they didn't have to have a model of the entire process. A precise mathematical representation. They could immediately implement this control system just using what they already knew, and then doing a few tweaks and testing, and they were able to make very, very high quality and effective rice cookers using fuzzy. So crisp is a term that tends to get used in the lexicon of fuzzy practitioners to describe values that are precise in terms of not having vagueness or some uncertainty associated with them. It's just that exact value. When you see crisp sets, that typically refers to Boolean or classical sets that are just binary. You can either have full membership or none. So we're going to go through a few more examples because we're going to start getting into how you then use that information to make decisions with it. Sorry, pardon me for one. So up above, we have this example of a crisp set that is describing tallness, and then another one describing short, even though we don't see this short set being described explicitly. And so whether someone is tall or not is being determined by this representation, where once they reach 180 centimeters, we'll say that they are tall. And if they're below that, they are short. And so this is this doesn't fully encapsulate a lot of the information that, or the continuum of shortness versus tallness that may actually be more useful. And so we can see another representation of this. This is somewhat like a sigmoid function describing the tallness of a person. And you can see that it starts ramping up quite a bit when we start getting around 175 centimeters or so, and then keeps increasing as you go further and further. And so instead of just saying someone's tall or short, if they're above 180 centimeters or not, we can then say how tall or how short they are based on their membership in that set, as defined by this function. And so in this case, instead of 179 right here being short and 180 being tall, we can say, well, how about 179 in this case? Well, 179 in this case is, we'll say 73% tall and 27% short. And 180, which is very close to 179, you would think they would share very similar characteristics in terms of memberships in those sets. Instead of being a drastically different representation, as in the classical set, you have a much more reasonable value where it says it's 74% tall and 24% short. Note that there are different characteristics for your representations based on the different characteristics of your membership functions. And we'll talk about that a bit more in a bit. Yeah, so the membership function embodies the mathematical representation of membership in that fuzzy set. The typical notation used for a fuzzy set is a set symbol with a tilde underscore, say A tilde, that's this right here. So this is the set that we're grading membership in, and mu that represents the actual membership in this fuzzy set A. And mu sub A is a function of x being the input value, the measured value that is coming in, and you're then mapping that onto its membership value in this set A. And so this is always in the range of 0 to 1. It can take on many different forms. There are a lot of rules of thumb about how to do this, but there are some characteristics that you need to have in fuzzy sets, and their membership functions that describe the membership. But one thing to know is that it doesn't necessarily need to always go to 1. It can be some subset within this range as well. But 0, it needs to be bounded by 0 on one end at least. But almost all membership functions that are developed do need to, or well, need is dependent on your application, but they will have some point in them where they get to full membership. Yeah, okay. So fuzzy numbers are another concept in here for dealing with uncertainty, and those are mapping the crisp or precise numbers to this vague or imprecise representation. So we can do this in different ways. You can see that there are different ways you can represent numbers where you can just have a singleton. You can have some interval number that we see here between 1.25 and 1.35. You can have other membership functions that are that describe a gradual increase between 0 and 1, like in this case is triangular, with having full membership at this value 1.3 where it's centered on. You could also have a combination of these. Like in this case, we have a trapezoidal membership function where we have this interval where we have full membership in the set. But then outside of these boundaries, 1.28 and 1.32, we see this gradation as defined by these linear segments where you have partial membership, but not full membership in that set. And all these are useful ways for representing these vague numbers or vague membership. I'm sorry, vague measurements that are coming in and still being able to utilize that information in practical ways. Some of those common membership functions, you'll see triangular membership functions quite often in the literature, and in most foundational texts for fuzzy, triangular is one of the most commonly used for a number of different reasons. Trapezoidal is also commonly used for the reasons that we mentioned previously, which is you can describe both a region that abides by the same behavior as a classical set, where it just has full membership over this interval in the input space, but then also allows partial membership outside of that to account for certain values that may be characterized as that set in some way, but not fully. Some of the other membership functions that are quite common are typically based on sinusoidal or Gaussian functions. Gaussians are typically used in a lot of situations where smoothness is required in the function for some reason. And those of you that are coming from the probability or state estimation world, Gaussians are, they have very important characteristics in terms of both smoothness and representation of that information in a lot of ways. So those are very popular as well. Some others, they're sigmoidal membership functions, polynomial membership functions. You can even have completely arbitrary non-standard membership functions that look like a number of a sequence of steps. We've seen quite a few of those in the past for particular problems. And the characteristics of the membership function are pretty relaxed. There aren't a lot of requirements for the properties of the membership function, typically aside from the fact that it needs to go from the range of 0 to 1. It is possible to have a membership function that doesn't have full membership, but those are really unique cases, and almost always the membership functions are typically required to at least have full membership at some point. So we're starting to get into fuzzy inference systems and having multiple membership functions that represent the input space. So what we've seen up until now in most examples is just a single membership function that represents a portion of the input space. But that's often the case that you have multiple membership functions because you're describing distinct regions of your input space, and you want to essentially do similarity metrics where you want to group portions of the input space together based on similar characteristics. So we've already used the short and tall example with one membership function. So this is another example with multiple membership functions. So let's go from, say, I don't know, let's say the low end here is 150 centimeters tall up through infinity, whatever the tallest person alive is. And instead of just saying a person is tall or not tall, well, we can describe different regions of their height more accurately. And so we can say, well, a person may belong to the set of short people if they are below, let's say this is 159 or 158 centimeters. They're just fully in the set of being short. But if they're in between that, if they're in between, say, 158 and 163 or so, they're in between short and medium height. We don't know exactly. There's some combination of the two. And so we can see that their membership decreases in the short set as you get taller and taller, and increases in the medium set until this point. And then from this region to this region, you're in the medium height set. And then the same thing going to tall. Once you cross over 175 centimeters, we're going to say you're more tall than medium. And obviously at this point, there's 0 membership in the short set because this goes to 0 around 163 centimeters. And then, like we said in the other example, once you're above 180 centimeters, you're just referred to as tall. So this is how you introduce multiple membership functions to represent the information in your input space more accurately, but then also what the overlap between those membership functions actually represents. And so you can exist in multiple of these sets at the same time. And in this case, you can only exist in two of these. There are certain cases based on the characteristics of your membership function. If you have Gaussians, for instance, you'll exist in all of them to some non-zero degree everywhere in your input space, and that's okay in many cases. There are other cases where you may want to define zero membership, and so that then leads into membership function selection based on the properties that you require of them. We can also have an example with triangular membership functions where we're talking about health. And so you may have some characteristics that are grading you as being unhealthy or healthy. In this case, maybe it's simply, let's say, calories that you take in per day, and 0 represents, well, let's go the other way. Let's say bad calories or whatever negative attribute in your diet you want to account for. As you go up in the scale, you're being more healthy. And so this allows you to capture that information using those fuzzy membership functions and have a mapping from, well, if you're taking in this amount of whatever it is, well, that's unhealthy. And so as you take in more and more or perform this action or whatever it is, higher and higher you become more healthy. But you can grade that more accurately. I'm going to skip over the Boolean and fuzzy logic operations. It's fairly interesting and important in terms of mathematical consistency and soundness, but we're going to pass over this for now. If people have interest in this, you can ping me after and we can have discussions. I want to move on, though, to fuzzy control. Pardon me, fuzzy logic systems, in particular fuzzy controllers, because this is much more directly applicable to what we'll be doing in XFC. So this is a fuzzy logic system, the main components, and in particular what we call fuzzy logic controller. In terms of control theory, what you typically have is you have some input coming in, almost always from sensors. You're getting feedback from the system in terms of sensor data. That sensor data comes in the form of inputs to your fuzzy logic controller. And your fuzzy logic controller then takes those inputs and puts them through what is called here a fuzzification interface, or it fuzzifies that information. And it does this by taking those measurements and evaluating the membership of those measurements in the sets in your input space. You then pass those sets, those fuzzified values, through your knowledge base or rule base or inference engine that then maps those fuzzified values on the input side to sets, fuzzy sets on the output side, or some action on the output side, I should say, some region in your output space. Because you typically have multiple of those, you have membership in multiple input sets, usually. That means that you typically have multiple output actions that can be selected. Those can then be defuzzified. Those are resolved into a final crisp output. And then that is what actually gets output back into your system. So the fuzzy logic controllers, or more generally, a fuzzy inference system, is just a mapping of inputs to outputs. So it's just a function, but it's taking in crisp input values and it's outputting crisp output values. But internally, it represents those in fuzzy ways that we'll see. So what does that look like using fuzzy logic? Well, we've seen that you have membership in a set. You can then associate those input sets with output sets, and you can represent those using fuzzy logic. So those control actions as rules might be something like, well, let's look at an example that has standard logic first. And in this example, let's say it's a heating system in a house. So in standard logic, it would say something like, if temperature is less than 68 degrees, and by the way, temperature less than 68, that is a classical set membership function, because if it's less than 68 degrees, then turn heater on. If temperature were greater than 68 degrees, it wouldn't have membership in this set. And so we wouldn't be turning the heater on. It would just be on or off. In fuzzy logic, you can represent this in terms of those fuzzy sets as described by membership functions. And let's say that the label on one of those was very cold. We could say if very cold, if you have membership in the very cold set, then more heat. Then your output action is to pump out more heat. We'll see a more detailed example of this, but what this really allows is for a much more granular control action than standard logic, while also accounting for vagueness in the input space. We may not have a precise measurement of temperature, but if we can represent the temperature in such a way that we can then say, well, it does belong to the very cold set, and we know that if it is very cold, then we need more heat. We can then perform this action, and we can represent that using fuzzy logic. So again, this is a fuzzy logic controller. We have a sensor that's providing input data, in this case, a temperature sensor, that then gets fuzzified. This is just a number of different membership functions. We have both triangular and trapezoidal. And once we measure our input and see where it falls in here, we can grade the membership values in each of these. We can then pass that to our inference engine, which has rules that say, well, if you're in this set, then I want you to perform this action on the output side, which means you belong in this output set. You then aggregate all of the active rules with their associated output membership functions, and you create an overall aggregate output action, and you then resolve that into a final value that then gets sent to your actuation. So these rules that determine the input-output relationships, these reflect expert decisions. I should say it refers to those expert decisions if you're encoding expert knowledge, obviously. Well, if these came out of something like a machine learning process, obviously they wouldn't. But regardless, it doesn't matter. These are rules that are associating inputs to outputs. In a fuzzy system, all rules fire to some extent. I actually disagree with this statement in some ways, and what I mean by that is it may not be the case that a fuzzy system that's being evaluated always will always reach all rules being fired. That's just not always the case, but certainly they need to be defined. They are defined as a conditional statement in the form of if-then. If a car run very fast, then the brake distance, apologies for the misspelling, the brake distance is long. And so you can associate these input sets with the output sets and actually form an English language sentence that actually describes the entire action that's being taken by the fuzzy system at that point. This is a very good visual representation of what's actually occurring throughout the entire process of the inputs coming in, the fuzzification, the rule association or inferencing, and then the output aggregation and defuzzification. So in this example, we have a 2-input fuzzy system with triangular membership functions on the input side. So this is a single a single measurement for X and a single measurement for Y. Those are 2 inputs, X and Y. We then have some output Z. And so this represents 2 different rules that are being fired in this fuzzy system. So this is the first rule, this line right here, and this is the second rule. So in the first rule, you'll see that the membership functions are being activated are different, by the way. By definition, they have to be. And so in this rule is associating this membership function for X and this membership function for Y with this output membership function for Z. So that's what the rule defines. If X is in this set and Y is in this set, then your output Z is in this set. Same with the second rule. The membership functions are just different on the input and output side. So let's go through the steps here. So we have this measurement in X. We see that our membership in this set in X is this high, and our membership in this set in Y at this measurement is this high. So we have these two different membership values, one for X and one for Y. We need to resolve those to calculate what we call our rule strength, the firing strength of that rule. In this case, we're using, so this is called a T-norm. In this case, we're using the product T-norm, or sorry, the minimum T-norm, which is one of the most common. So we're taking the minimum of these membership values and using that to scale or truncate our output membership function, because that directly equates to the contribution that output membership function will have on the overall output. And this output membership function is also triangular because we're using minimum. We're just going to truncate it at that point. And so the result is this trapezoid shape. And that is the fuzzy output of that rule. We then do the same thing for the next rule. Because they're different membership functions, they have different membership values. In this case, Y is still the minimum, so the Y membership function is determining that rule strength firing. And we get this value, we truncate the associated output membership function to that level. We then get this aggregate, the contributions from all the active output membership functions after being scaled by the rules. And so we get this overall distribution. This represents the actual output of our fuzzy system. However, we still need to resolve this to a crisp output action to then send to our actuators to perform the action, because you can't just send an entire distribution. One thing to note here, though, is what you see, though, is based on how you resolve this to a singular value, you will likely have much higher contributions or higher contributions from this rule that had a higher firing rule strength. And so that's what allows you to capture the importance of each rule. And that comes from those membership values. So how high your degree of membership is on your input sets determines the importance of that output action on the overall output. There's a number of different ways to resolve that output distribution into a singular value. Most commonly, it is some form of a centroid or center of area or center of gravity calculation, which is a weighted average representation of the contributions of each of those individual pieces in that distribution. This is another representation of what we just saw, and this is going back to the temperature example where we say, well, we have this measurement come in right here for temperature, and that temperature has membership in the cold set of 0.7 and membership in warm of 0.2. So immediately we know that the rule for cold will be firing at a higher level than the rule for warm. We then have these rules that say if temperature is cold, so if we're in this set, then the valve is open. The valve, that does whatever in the system to increase the heat, we'll say. And so we have rules that describe the input to output relationship between all of these sets. In this case, it's just a single input and a single output, so we just have a one-to-one mapping. We just have 3 rules. And so we say if the temp is cold, then the valve is open. It's in this output set. If the temp is warm, then the valve is half open. It's in this set. And if the temp is hot, then the valve is closed. We're in this set. We can then calculate, similarly to what we saw before in this case, we can calculate the rule strength firing. In this case, we only have one membership, we only have one input, so we don't have to do the minimum. It's just that, well, the minimum is that value. And so we truncate our output membership functions at those points. And we get this overall aggregated output distribution. We can then resolve that into that final output for where the valve should be between fully opened or fully closed based on that. And so we'll be somewhere here on that where this represents fully open and this represents fully closed. What we're seeing here, these are called Mamdani fuzzy systems, where Mamdani fuzzy systems are defined where the output sets are also fuzzy sets. They have membership functions that are non-singletons, whereas non functions, but they are actual fuzzy sets. And so there's another type of fuzzy system typically called a Takagi-Sugino or Takagi-Sugino-Kang system that uses different types of output functions that are not fuzzy sets explicitly. However, we're going to focus on Mamdani for the time being. Another example is this one where we're talking about insurance for cars based on the age of the person that is getting the insurance. And so this is an example where we have rules that determine what the risk level is based on the age and the power of the car. And so we have one rule that describes different associations based on the portions of the input space. So in this case, we're saying the first rule is saying if your age is young, if you have membership in the young set, and your car power is high, it has membership in the high car power set, then the risk is high. You have membership in the output membership function that represents high risk. Similarly, if your age is normal, or in this case, we'll just call it middle age instead of normal, and your car power is medium, then your risk is medium. And you would define all of these rules for every combination of input membership functions. So you would also have rules if you had a fully defined fuzzy system that said if you're young and your car power is medium, then your risk is X, is whatever output. And similarly, if your age is normal, or if you're middle age and your car power is high, then your risk is X. And so you would fully define all those rules, and so you'd have a full input to output mapping of the entire input to output space. This is going through a similar example. I'll leave this because we've already gone over this quite a bit to this point, but you'll see similar things. You look at the membership values, the rule firings, the strength, use that to truncate your output membership function that's associated with these inputs. You create your entire aggregated output distribution, and then you resolve that into a final value. Like I mentioned, one of the most common defuzzification methods is center of gravity. This is a lot of the default in most fuzzy toolboxes. One problem with center of gravity, in fact, the main problem with center of gravity is the complexity of doing that calculation. You have to do this integral. So a lot of people approximate it in different ways. So one way you can do this is by discretizing it and doing the Riemann sum or some other representation of center of gravity that is a much faster approximation. Again, you may not have the full precision of the center of gravity, but this is a designer choice because it depends on the properties of the system that you're trying to develop. And a lot of times the approximate way is the best way. I will highlight that there's a number of different defuzzification methods out there. including ones that then resolve the output to a discrete set. You don't have to necessarily have a continuous output. You can have defuzzification methods that do give you different discrete outputs based on where you are in the input space. And so some of those you'll see in the literature, and fuzzy resources are, mean of maximum. You'll see weighted average, which is more akin to a center of gravity. It gives you a more continuous output. But there's a number of different things you can do to defuzzify your output distribution based on the properties you're looking for. So that is fuzzy logic and fuzzy systems. One last thing I would like to go over are fuzzy trees. And the reason I want to do so is because you may find this useful in practical terms for developing your AI system. One reason why fuzzy hasn't been used as widely as other types of function approximators, like, say, neural networks, is because they've suffered from scalability issues. And the reason being is, if you recall, I mentioned that your rule base that has to be defined has to be fully defined for all of the combinations of input membership functions. So if you do the math, what that means is that your rule base, as you increase the number of inputs, keeps expanding exponentially. And so the number of parameters that you have to define for a fuzzy system is extremely sensitive to the number of inputs. If you're defining a fully conjunctive rule base, there are, of course, other ways to get around that, depending on what you're doing with your inferencing. But by default, the number of inputs heavily increases the complexity of fuzzy systems. So one way to get around that is to limit the number of inputs to a particular fuzzy system. And so fuzzy trees, which are an extension of cascaded fuzzy systems, are a way to do that. Cascaded fuzzy systems are systems where you have multiple different levels of fuzzy logic systems that are hierarchical, and you have data that gets passed into one or more fuzzy systems. The output of those fuzzy systems are then passed into additional fuzzy systems. And it's called cascaded because it's typically this hierarchy in somewhat linear fashion, where you keep the individual number of inputs small in each of your fuzzy systems, but you're still able to account for higher dimensional data by adding more fizzes and combining the outputs from a fizz, which is lower dimensional than the input data, almost always, into the subsequent fizzes. One issue with cascaded fuzzy systems, though, is if there's heavy coupling or you have dependencies in your input value, in your different inputs, it's hard to account for that in the different fuzzy systems. And so you can hurt your approximation capabilities by not being able to fully represent the coupling there between those variables. Fuzzy trees were introduced to help mitigate that. They remove those directionality or structural assumptions of typical cascaded fuzzy systems. You can even have things like feedback. You can have lateral connections between fizzes. You can also hybridize this much more easily with other systems, such that you can have different nodes that may or may not even be fizzes. And so this is really a way to both scale up a fuzzy system, being able to take in a much larger number of inputs, while also retaining that approximation capability as much as possible. The performance is bounded above by a single fizz. If you had a single fizz that took in all of your inputs and had as many membership functions as you wanted, of course, it would be a very accurate approximation, but the number of parameters you would have to define to do that would be enormous. And so fuzzy trees really cut down on this. To give a concrete, non-notional example, this is a fuzzy tree that was developed for an air-to-air combat collaborative firing decision-making system quite a few years ago. But this is an example of a system that takes in, a number of different variables. So in this case, we have, well, we have 15 inputs coming in, and a fuzzy system taking in 15 inputs. The number of rules you would have to define to fully map that input-output space would just be completely prohibitive towards even evaluation, not even machine learning or any other type of thing. Even evaluating those systems can be extremely expensive when they become that large. And so being able to resolve these down into a fuzzy tree like this is very effective, because not all information is going to be relevant to all other information. You may have variables, like in this case, that are associated with each other, but not with anything else. And so you can group them together, combine those, pass those through a FIS, take the output from that FIS, and combine that with other information, and then keep going down to resolve that to a final action. And so what we see here is, you're taking in a number of information about different targets and platforms, different distances. You're then, these red, by the way, these red polygons are the FISs themselves. The blue boxes are the input values. And so we have this many FISs, this many fuzzy systems that only take in 2 to 3 inputs. So they're all relatively small in terms of their rule base, but they're still very effective in approximating the overall mapping, because they're only taking in relevant information and combining that with the output information coming from previous FISs. And so those FISs are both doing input to output mapping for decision making, but in this case, it's also doing dimensionality reduction. So it's doing both. So you're really compressing these pieces of data into some other representation that can be more effectively passed through the system to be more efficient. So this is the end of the slides for the intro to fuzzy logic and fuzzy systems, including fuzzy trees. We're going to open it up for discussion. I do want to tailor it a bit towards XFC, in the sense that this is directly relevant to a lot of what you'll do in developing your agent to play in Kessler, because you won't be able to take in, let's say, information on all the asteroids. There are some scenarios where the number of asteroids is in the hundreds. So obviously you won't be able to take in hundreds of input values for every different asteroid and calculate something based on that. A fuzzy system that takes in that is just going to be completely out of the question, a single fuzzy system. However, there are things you can do, including fuzzy trees, to reduce the amount of information you need to process. But then also internally, how you represent that information, you can do it in a much more compact and efficient manner. And so with that, I will open it for questions. I will also say that there will be an associated milestone that you need to complete that is based on this. We'll give those details, though, after the Kessler introduction in 2 weeks. So don't worry about implementing anything or having to do a milestone yet, but you'll receive more guidance and more details on those milestones at that point. And in addition, there are a number of different toolboxes out there for implementing fuzzy. Feel free to write your own. In fact, we encourage that, because not only will it help you learn, but oftentimes you'll find that you can make one that's much more efficient than the standard off-the-shelf options that are out there. However, if you want an off-the-shelf option, one of the ones that we recommend is skFuzzy. skFuzzy, which is scikit-fuzzy in Python, is a relatively capable toolbox that is relatively fast compared to a lot of other options that are out there. Of course, it's not the only one. Feel free to use whichever that you want. But yeah, this is one of the better off-the-shelf options that gives you a lot of flexibility, has a lot of features, but also is relatively fast. So with that, I will open it up to questions or comments or anything else from the audience.
I had a question about when you showed some of the for the fuzzy controller, some of the rules systems. Most of the ones you showed were taking the minimum of the of the memberships. And that's for and I suppose for or it'd be taking the maximum.
Correct.
Would there be like any situations where it'd be something other than like the minimum or maximum?
Yes. So if you're interested in that for the AND operations, if you're defining your rules by conjunction of input sets, if this and this, then this, as opposed to, the disjunction if you have this or this, those are called T norms and T conorms. If you look it up, there are a number of different ones depending on the properties that you're looking for in your system, or if you have some other justification for using them. Minimum is the most typical one that's used, and it is also the see if I remember correctly, it is the one that represents the maximum value for the T norm. It has a higher value than the other T norms, and similarly with max for the OR operations. And what I mean by that is if you did the product T norm, which is another one you can use for conjunction for and, obviously you'd be multiplying these together, so you would be getting a value in between. As opposed to min, which is, or sorry, below, which is minimum represents the max value. So it's giving you the max contribution for that rule, as opposed to something like product, which will give you a lower contribution, which gives you different properties. On the OR side, similarly to product, there's a probabilistic OR, which is similar to the calculation you would do for disjunction in classical sets, where you have the addition of the values and then subtracting their product. So yeah, and those aren't the only ones. There are some. This is a subfield that has all sorts of research into it because of the properties that come out of the system. So I encourage you to look at all the different options. In most fuzzy toolboxes, you'll probably only see product and min, or on the probabilistics, or sorry, on the OR side, you'll probably only see probabilistic or maximum. But yeah, does that answer your question?
Yeah. Thank you.
Sure. Yeah, one of the important characteristics that you may get out of something like the product T norm, where you multiply these values instead of taking the minimum, is that it lends itself to getting much more continuous behavior, whereas min, you can get discontinuities in the output space sometimes. Of course, that depends on your membership functions as well, but yeah. Okay. Well, if nobody has any other questions, we will go ahead and end the seminar for today. As always, please ping us if you have additional questions. Again, I'm going to reiterate, please join the Slack if you're competing and you haven't done so already. Feel free to email us as well. This will be recorded and put up on the YouTube channel before the end of next week, and also the kickoff slides. That seminar will also be put up soon, definitely before the end of next week, probably before the end of today. And so anybody that missed the kickoff as well, that will be uploaded. All right, well, that concludes the first seminar, the fuzzy seminar for XFC 2024. I'm excited to see what everybody comes up with, and yeah, thanks for joining. Bye, everybody.